We're now recording.
Yeah. So at first, let's wish Dr. Z a full and speedy recovery. And as for the Peaceable Queens problem, actually we have an expert here, Dr. Neil Snow. So here we should have some. Okay, so first let's look at what is the Peaceable Queens problem. So the problem is that what is a maximum number n such that it is possible to place n white queens and n black queens on an n by n chessboard so that no queen attacks the queen of the opposite color. So we have some pictures from Dr. Stone's paper. So this is for 5x5 board. At most, we can place 4 white queens and 4 black queens. And this is just one of 3 solutions. So anyone can come up the rest 2 solutions? I think Dr. Stone must know the rest 2.
Yeah, but not offhand.
So this is a solution for 8 by 8. And then a conjecture solution for 20 by 20. Actually, these two look quite similar. Right? And this is a general construction by Jubin. So it says that for a very large board, this one might be the optimal one. So for this one, for each color, you have 2 pentagons. Okay, so then let's watch a video by Dr. Sloan. Oh, before that, we only know 15/10 of this sequence. So it means if the board is 1 by 1 or 2 by 2, there are no ways to place any white queens and black queens such that a queen doesn't attack a queen of the opposite color. So here we have a video.
Your financial life, it has so many pieces, but now there's personal capital, the free way.
If you go to a bigger board, then chess queens are trained to attack on sight. They see a piece of the other color, they capture it. That's their job. Those are normal queens. I want to tell you about peaceable queens. The question is, you have a chessboard of a certain size, it could be 8 by 8 or it could be 4 by 4. You want to put down as many queens as you can. Some black queens and some white queens, and they must not attack each other. 2 constraints in this problem. Equal numbers, as many as possible, and they do not attack queens of the opposite color. So this is a problem that Don Knuth told me about in 2014. And I like the problem a lot because it has some lovely pictures. It's an easily stated problem, and we don't know much about it. And there's a really incredible conjecture. Suppose we have a 4 by 4 chessboard, and we want to put down black queens and white queens so they don't attack each other. So if you put 2 black queens in the 2 corners and 2 white queens in the 2 middle squares, the black queens do not attack the white queens, and the white queens don't attack the black queens. The most you can put down is 2. There's no conflict when 2 white queens can see each other. Here, the white queens want to avoid being seen by the black queens and vice versa. This is a lovely problem because it's really, really hard. We know very few terms. So let me show you what we actually know about this. So for a 2 by 2, if you put a black queen here, it attacks the other squares. For a 1 by 1, you can't do anything. So what we know is that for a 1 by 1, the answer is 0. For a 2 by 2, the answer is 0. What about a 3 by 3? If we put a black queen here, it attacks all the squares except these 2. So we could put a white queen here. We could put a white queen here too, but we have 2 white queens, and we cannot put 2 black queens. So the numbers have to be equal. Okay. All you can do is 1. 1 of each color is the max. 4, it's 2. 2 is the most we can do. So what about 5? There are actually a lot of solutions to the 5 by 5, but there's one which is overwhelmingly nice. And you put 4 at the corners, and you put 4 in the other obvious places. There, 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 and there. And you see, they cleverly avoid each other, and you can't do more. So for 5, the answer is 4. For 6, you can do 5. And for 7, I think you can do 7. On a regular chessboard, you can do 9. 9 black, 9 white, and they don't attack each other. And you notice they come in clumps. And that seems to be a very good way to do it. If you go to a bigger board, then for 9, we can do 12, 10, 14. For an 11 by 11 board, you can put 17 black queens and 17 white queens. 12, 21, 13, 24. And very recently, just a couple of weeks ago, someone found the next term, which is 28. Beyond this, we don't know. You can use things like simulated annealing to run to get lower bounds, to get things that look pretty good and maybe optimal. And you can use integer programming to get upper bounds, to show that you can't get more than such and such. But the exact value is not known beyond that point, although we have some conjectures. So here is a very plausible looking solution, which has 58 black queens and 58 white queens on a 20 by 20 board. And this is a construction which says if you generalize this and put the queens into 4 5-sided clumps, a clump here, a clump here, a clump here, and a clump here, then you can do very well as we know. In every case we've looked at, except one small case, the answer is at least 7n squared over 48 for an n by n board. So 4 clumps, which are 5-sided. This picture here shows the general situation. Now, could this really be optimal? We don't know. I think it's a beautiful question. So I run this collection, this database called the Online Encyclopedia of Integer Sequences. And when we got to 250,000 sequences, it's not that much, but to us it seems like a lot. All different, all interesting, hopefully. They're all numbered. So when the first one is A1 and A2, normally they come in every time a new sequence comes in, it gets the next free A number. And we were around 250,000. So we had a competition to see which would get the sequence number A, 250,000, A250000. I collected the votes. I did what is traditional. I made my candidate win. And here it is. Lovely problem. Another amazing conjecture. Could this really be the right answer? Is this when God is playing chess with the universe? Is this where he puts his peaceable queens? It could be, or it could not be. It's a toss-up right now. Hopefully we'll get more data. You know, what I would do if I had a team of assistants, I'd pick, say, a 30 by 30 board and use some hill climbing method or hook jeeves, pattern matching, optimizer to find. You set it up as an optimization problem. It's an integer programming problem. Maximize the total number subject to the constraints. And the constraints are for each row and column, diagonal. You don't have black and white on the same row.
So I've been looking at Brilliant, today's episode sponsor, for some chess-related puzzles, particularly.
Okay, so in our paper, we look at the problem as a continuous problem. Should I erase this?
No, erase.
So we look at the unit square, U equals to a unit square. So we want to find out the region of white and black queens in this unit square. So let's say that W is the region for white queens. Then the region for black queens B equals to the point in a unit square such that for any point in W, x is not equal to u, y is not equal to v, x plus y is not equal to u plus v, and y minus x is not equal to v minus u. So I think this definition is intuitive. It just means they are not on the same horizontal line. They cannot be on the same vertical line, and they are not on the same diagonal. Actually, it doesn't have to be diagonal like this. It can be any 45-degree line like this, or 135-degree line like this. So now the problem becomes that we want to maps over all subsets of U the minimum of the area of white queens and area of black queens. So this is our goal in this problem. So first, let's look at Jubin's construction. We cannot prove this is indeed an optimal one, but we can show this is a local optimal case. It means that we assume these two regions have similar shapes like this. There are two pentagons, and then we can just use variables. We can use letters for the side length. Then we want to determine the side length. And it turns out that the side length is exactly the same with Jubin's construction. So it means if we have two pentagons like this, Jubin's is the optimal case.
You're assuming that one of them has a corner of the square. What do you assume about the positions of the pentagons? You allow the
No, we must put one of them here.
Sorry?
In the corner.
One corner is in the corner.
Yeah.
And what about that one?
Which one? You mean this one?
How is that anchored?
Oh, so you mean
You assume that it starts at position 1/2?
No, we assume G0. So you can see that there are parameters here. Theta is 0, 0. So for this side, the length is square is root 2 times a. That means the coordinate for this point is AA.
Okay.
And then this one is b minus e. So for this point, it will be a comma a plus b minus e. So
Okay.
this side length is e. So this one is root 2 times a minus e. And for this one, this is b.
So you have 3 degrees of freedom?
No, I think A, B, C, D, E, F, G, I think 7. So we have 7 degrees of freedom.
And that's G. Okay.
Yeah, that's G.
Thank you.
Yeah. So we have the coordinates of the white. For the white one, it will be 0, 0. A plus B minus E, A minus E, A plus B minus E, 0 B. So this is the coordinates for the left white queens, and for the left one. For the right one, So similarly, we can also have the coordinates for the black pentagons. And then, of course, we have some restrictions for the parameters. So we need to figure out the restrictions. So for restrictions, for example, this one, the x index, the x coordinate is g plus c. So g plus c must be less than 1. So it's quite straightforward to get those constraints for these parameters. So once you have these constraints for the parameters, now we look at the area. So the area for white queens is much easier to. It's just AB minus a half E squared plus CD plus a half C squared minus F squared. The area for the black queens is quite complicated. It's really long, so maybe I want to write all of it. So generally it has 29 terms. So we want these two areas to be equal to figure out the value of these parameters. So when they are equal, we find that for the white queens, the parameters is the origin, a quarter, half, 1/6, half, 0, 1/3. This is the left pentagon. And this is a right pentagon of white queens. So similarly, we have coordinates for black pentagons. So this is the left one. And this is the right one. So all three results can be obtained by Lagrange multipliers. And with these parameters, these coordinates, you can find that the area of either color queens equals to 7/48. So that's why Jubin's construction is a local optimum. And actually, Doron Zeilberger informed us that this construction already appears in Stephen Anley's book in, I think, 70s, right? Mm-hmm. Yeah, so actually it has been found maybe 40 years ago. So since it's difficult to solve this Peaceable queens problem, we want to do some easier case. So for the white queens, we started from the single component, connected component. So first one is, what if the white queen has a single rectangle area? In that case, what is the optimum case? So this is a much easier question. So this one is the best when there is only one rectangle for white queens. And this case is quite easy to solve. So let's assume the length of the two sides is A and B. B is two lines. So this area is attacked by this rectangle. And then the same is this area. And this area. So it means if we have one rectangle of white queens with side lengths A and B, then black queens can only be put in these two triangles.
That's nice.
So actually, these two triangles, they should be the same. The picture is not good. So the area of white queens is A times B, and the area of black queens is a max of 1 minus A minus B and 0 squared. Because if A plus B is greater than 1, then actually all this plane is attacked by this square, by this rectangle. So when they are equal, we can find the best A and B. So it turns out that A equals to B equals to 1/3. So in this case, the largest area is 1/9. So rectangle is the easiest case. Then we want to move to a single parallelogram. So picture is like this. So in this case, we let the parallelogram for white queens be 0, 0, A, A, comma A plus B, zero, comma B. So this is the white queens. Then this area is attacked. Same for this area. So in this case, we still have two triangles left, and you can put black queens in these two triangles. So anyone can guess the optimal A and B in this case? Yes?
1/3 and 1/3 based on the diagram?
Yeah. Yeah, actually that's the same because in this case you can find that the length of this triangle is 1 minus A minus B if this is non-zero, if this is positive. So in this case, we have exactly the same formula. So we let the area of white parallelogram equals to the area of the two flat triangles. Then we will have the same answer. So in this case, the answer is 1/9 for the area. So then we move to triangle. So how about there's only one triangle? Any guess for the triangle case? If you have only one triangle, should it be larger or smaller than one rectangle?
Smaller?
Actually, it's larger. Yeah, so this case. So if you have one triangle, of course you want to put it near the corner. So maybe there might be several ways to do it. One way is to put a triangle like this, but this is very wasteful. If you put it like this, then you will find that for this area, it's totally wasteful. So why not just add the other part? So we don't want to put a triangle like this. So let's assume this is A. So this is A, comma A. If this area is attacked, so it's this area and it's this area. So it means the black queens can only be in this part, in this triangle. So the area of white queens is 1/2 times A squared. The area of black queens is 1/2 times 1 minus A squared. So we can see that A equals to 1/2. So the area equals to 1/8. So now we'd like to think that if there's only one component for the white queens, what would be the optimal case? It doesn't have to be a rectangle or a triangle. So first we think that it should be some kind of octagon at most. So why it should be octagon at most? Because we can see that when the queen attacks the other area, it might be horizontal or vertical or some kind of diagonal. So it means if you have some shape which is not octagon, it might be wasteful. So in this case, if we have an octagon, of course we want to put it near the corner. So at most, we can assume something like this. So we need several parameters. So from this picture, you can see that here it will be wasteful. So we don't need this one. And it's the same for this part. We can simply adding this triangle without adding any attacked area. So it means we can assume this is a hexagon. So then we assume we have a hexagon, we want to find out the optimal hexagon.
Can you make that rigorous? That it has to be an octagon if there's only one component? I mean, it's obvious the way you say it, but
yeah,
do you actually prove that an octagon is optimal if you only have one component?
No, actually we didn't prove that. So this is a simple hexagon. So we need 4 parameters in this case. This is A0. This is A plus B, comma B. So it means this third length is equal to 2 times B. This third length is C. So this one is A plus B, comma B plus C. And we let this one be D, comma B plus C. Then this coordinate will be 0, comma B plus C minus D. So in this case, the area for white queen is A plus B times B plus C minus a half times B squared plus D squared. And the area for black queen is a half times 1 minus A minus B minus C squared plus half times 1 minus A minus 2B minus C plus D squared. So when A equals to C equals to D, so when they are half, when A equals to C equals to D and B equals to 0, we have something similar with the triangle one. And when A equals to B equals to C equals to D, in this case, we have, this is a triangle. We have 3A squared equals to 1 minus 3A squared. So we have A equals to 3 minus root 3 over 6. So it's a round point to 1. Then the area is 3A squared, which is around 0.13. So this is larger than the triangle case. So then we want to think about what if there are two components?
What's the answer? I'm sorry, I couldn't quite read. So with this case,
yeah,
what do you get for the best value?
Oh, A equals to 3 minus root 3 over 6. Then the area is around 0.133974. So if you want the precise formula, the area is 2 minus root 3 over 2.
Thank you. So it's better than 1/8.
Yeah, it's better than 1s, because 1s is 0.125. So now we want to think that if there are two identical squares. So why did we choose two identical squares? Because they have relatively fewer parameters. So in this case, we only have two parameters. The first one is the set length. The second one is the location of the lower left corner of the right square. So it's generally it's easier to do this. So let's say the set length is A. And for the right square, the coordinate for the lower left corner is s, comma 0. So from this we can see that a must be less than s. So actually, when we choose different a and s, the shape for the black queens can be very different. So that's how experimental math is needed. So I did several experiments to find out the nearly optimal cases. And then around the nearly optimal cases, we can see that black queen should be like that. So then we can have a formula for the area of black queens. And of course, A is less than half. So the area for white queen is just 2a squared. And for black queens, it depends on several cases. So it means that the domain is separated into 4 regions. So we know A is less than a half, and S is greater than A. And of course, S should be less than 1 minus A. So it means this is the possible case for the values of A and S. And we need to look at 1 minus S minus 2A and S minus 2A. So S minus 2A is just this line. And 1 minus S minus 2A is this line. So now we can see that there are 4 regions. In each region we have a formula for the area of B. And our goal is to let these 2 areas to be the same. But since in different areas we have different formulas for B, so we need to do this for each area. So the result is quite complicated. We need to use the, let's see, I think it's called cylindrical algebra decomposition. We need to use that to find out the values. How much time do I have?
8 minutes.
So there are 4 cases. When A is greater than 2A and is greater than 1 minus 2A. So by cylindrical algebra decomposition, we have that so it also depends on the value of A. And when s less than 2a and s greater than 1 minus 2a, the result is empty. When s less than 2a and s less than 1 minus 2a, then we have a is in this region, this interval. So in this case, because we want to maximize the area, so it means we want largest A. So which A is the largest one here? In this case, so the largest A is here. It means we need to use this A and this S. So if we plug in this A and this S, we can find that the area equals to a rational number, but actually this is not large, it's quite small. So it's smaller than the hexagon case. So similarly, we also want to think about the two identical isosceles right triangles. Because in this case, with the same orientation, we still have two parameters. So, and we also use cylindrical algebraic decomposition. So in this case, we find that when A equals to a quarter times 3 minus root 3, we can maximize the area. And S equals to a half. But this area is smaller than the previous one. And we can also do this for the opposite orientation for the triangle. So for this case, we don't need cylindrical algebraic decomposition because the area formula for the vacuum is quite easy. So in this case, the area is for A equals to so the area is 1s in this case. So finally, we think about this case, we have one square and one triangle. They have the same side length. So in this case, we also need the cylindrical algebraic decomposition. And there are two cases in this configuration. So the first one, when there are two squares, it's more complicated because there are 4 regions in this case only two regions. And we find that when A equals to this number, the area is maximized. So in this case, the area is approximately equal to 0.1144. So it means this case is better than the 2 square case. So with similar ideas, actually we can do maybe more squares or maybe rectangles with different set lengths. But in that case, we will introduce more parameters. So for the cylindrical decomposition case, it might be more difficult. So we haven't tried, but if you are interested, we encourage you to try those cases. Thanks for your attention.
Right.
Yeah.
So, what is the best known upper bound, and do you think that the truth is closer to that or to the 7 over 80 or over 48?
You mean in this kind of configurations, like two components?
Or in I guess upper bounds in either case, either the specific 2-figure or upper bounds for the general problem.
So, because the best we already know is 7 over 48, which has 2 components. Both of them are pentagons. So that's the best case we know.
So if that's not just the best construction we have, that's the best construction that's possible if you only have 2 components for white?
Yeah, it might be. Yeah, but we don't know actually.
Right. So my question is, what do we like? What is the best upper bound that we do now?
You mean not including that one?
Is that the best one that we know?
Yes. The Jubin's construction.
Well, that's a lower bound, right?
I don't think we have a good upper bound.
No.
Oh, you mean? Oh, I see. I understand your question. You mean because we already know that that's a lower bound.
Yeah.
Yeah, I don't know about the upper bound, but that's the best case we have so far.
Okay.
Everything I know is in the A 2500000.
Yeah, when more parameters are introduced, this problem gets quite complicated. I tried 3 squares. It seems that if there are 3 identical squares, the area is more than 2 squares.
So what are the computational problems to trying like a rectangle? Like what problems do the new parameters introduce?
So if you have a rectangle, then you have 2 different set lengths.
Right.
Then you introduce 1 more parameter.
Right.
So when you have more parameters, you have this kind of formula. You want them to be equal. Since there are more parameters, it's difficult to solve them. And the cylindrical algebra decomposition gives you the first, if you have only 2 parameters A and S, it can give you the range for either of them. Then it can express the other parameter as the function of the first one. But when you have more than 2 parameters, the problem is that the formula for the area might be a function of more than one parameter. In that case, it can be more difficult. Because now here you see it's only a function of A. Then it is quite easy when you do the cylindrical algebra decomposition. First, you find the range for A. Then you can know which is the largest. You know the largest area. But when this is a function of several parameters, in that case, even if you know a range of some parameter, you are not sure which case will be the best. So that's a difficulty when you introduce more parameters.
All right, let's thank Yukun again. And Yukun, do you mind if I post the video?